Today we are going to do an experiment. The aim of our experiment is to verify the laws of combination of resistances. The resistances that we are using are R1 and R2. What is the principle of our experiment? That is Wheatstone bridge, and a meter bridge is a modified form of that. So, let us see what is the apparatus that we require. We need a battery eliminator, we need a key, a rheostat to adjust the current in the circuit, our meter bridge with terminal A, this broad strip with a gap E to connect a resistance, point B where we will connect the galvanometer and the jockey. In gap F, we have a fixed resistance box. We can choose different values from this to take different readings. The thick strip bent at 90 degrees takes us to the other terminal at the end of this wire AC, and this terminal is connected back to the eliminator. So, our circuit is complete this way. Let us see what formula we are going to use. The resistances, when combined in series, the resistance of each one of them is added. You can have as many resistances in series and you just have to add them all up. That is what the law says. If you were to combine it in parallel, that the net resistance reciprocal is equal to reciprocal of each of these resistances added. That means, reciprocal of R1, reciprocal of R2 will give us the reciprocal of the net value of resistance. How will we determine this value? The formula remains the same as before, and you can use the formula as we had done earlier in our meter bridge experiment when we were finding the resistance of the wire. The resistance net will be given by R into AD upon 100 minus AD. This, according to our circuit, will be like this, and we have the AD value as read off from the scale, and 100 minus AD is not difficult to find. So, let us start to do our experiment. We will connect R1 in the gap E, because we will first find its resistance. Having connected this, our circuit is complete. We turn on the eliminator. We will put the key so that the circuit is complete and the current flows through it. The next thing to do is to take out a suitable resistance from this resistance box. This is only a guess that the resistance value for R1 would be, let us say, 5 ohms, 6 ohms, 10 ohms. So, we can take with, say, start with 5, it could be any value. Taking 5 out of the resistance box, we take a jockey, hold it at two ends of this meter bridge wire, check out for deflection. This deflection at the moment is to the right. On the other side, when we place this, the deflection should be on the left. This means somewhere in between here we will get our 0 deflection in the galvanometer. That means, we are trying to achieve a balanced Wheatstone bridge, so that we can use it to find the resistance R1. Setting out to do that, let us gently move the jockey on the wire. As we take this along, you can see that the value of the deflection in the galvanometer is reducing, and it is 0 right now. We have to write these readings down. So, we take our observation table, and this value is 46.5. So, in our observation table we write the value 5 ohms from here, length AD is 46.5 and we are ready to take the next reading. All you need to do is to say take out 6 ohms from the resistance box, look for 0 deflection again on the wire, gently move it along. Remember never to press the jockey hard on this. Looking at the galvanometer, this is the value for AD, where the deflection in the galvanometer is 0, and we read this as 39 centimeters. Make a record in your observation table 39.0, because the least count of the scale here is 1 millimeter. So, first place of decimal should be taken into account. For the next set of readings, shut off the current in the circuit. Instead of R1, connect R2 in the same gap and repeat the experiment, connecting R2, and the connections should be tight without changing anything else in the circuit. Everything placed the same way. We can again get the circuit moving. Again take out say 5 ohms. This is assuming that this value would be around 5, 4. The variation should not be too much in our guessing, because then you would get deflection on the wire, 0 deflection on the wire somewhere towards the ends of the wire, which is not such a good thing to get the balance closer to any of the two terminals A or C. Let us see now again where the 0 deflection or null deflection is obtained in the galvanometer. See carefully, this value is 44.5. To take the next reading with R2, supposing we take out 7 ohms from our resistance box, it does not matter, and we look for 0 deflection again. Carefully take these readings, and this value is 40.8. Make a record of the same in your observation table for R2. Next, what we have to do is combine both R1 and R2, but this time in series. That means both of them have to be used. I hope you can see how this becomes a series connection in gap E. E, the current goes to R1, to the next terminal the connection to R2 and back here. So, both the resistances R1 and R2 are connected in gap E and in series. If we are to take readings again, from our knowledge, previous knowledge, we know that the resistances when combined in series, they add up. So, if one was approximately 5 and so was the other, it is justified to take out say 10 ohms from our resistance box, 15 ohms or maybe 11 or 12 ohms, so that we are not looking and hunting for the null point on this meter bridge wire. So, I take out for convenience a 10 ohms from the resistance box and plug in my key, look for the balance point, balance location on this wire by again moving the jockey gradually and slowly, watching for the deflection in the galvanometer, which should become 0 at the null point or balance point. We need another observation table for this, because that is what will allow us to calculate the combined resistance of these two. That will help us verify whether the R1 value added to R2 value gives us the combined value of R1 and R2 as predicted by the law of combination. So, this reading we had just taken. Another reading can be taken likewise, say we take out 7 ohms here. Again look for the null point. And we have got our null point at 58.3. So, we make a note of that. So, the resistance that we have selected is 7 and 58.3 is our balanced length A D. The next thing to do is to combine our resistances in parallel. How do we do that? I will just show you R1 and R2, they are connected in parallel. Now, when we connect the circuit again, we are looking for the combined resistance of R1 and R2 when connected in parallel. From our previous knowledge, we know that this value would be less than any one of the values. So, if we found one value to be approximately 5, how did we get that? Because for 5 ohms from the resistance box, our null point was obtained close to 50. That means the wire was divided almost in half. That means these two resistances should be nearly equal, which means when they are in parallel, they should be less than 5. So, there is no point taking out higher values of resistance from our box here, and we can select say 1 ohm, 2 ohms and find the null point. Looking for the null point, let us slowly move along the wire, watching out for our galvanometer somewhere here. So, our length AD at the moment is 69. So, we can make a note of all these readings in another set of observation table. You will say we have to go on making so many observation tables. Well, yes, because R1 and R2 separately. So, 2 observation tables for the 2 resistances, 1 observation table for them being in series and 1 observation table for them in parallel. We take out a 2 ohms and take another reading for it. Carefully watch your galvanometer, and that is our balance point. So, again reading off from the scale, it is 54.3. Any guesses as to what this combined value is? Because it is close to the center, 54 is close to the center, the 50 being the half of 1 meter. So, 54 is close to the center, that means the combined value of the resistance must be working out to be close to 2 ohms. That means, when you accurately calculate this using your formula, you will be able to justify and find out for yourself whether actually R1 and R2 or any 2 resistances when connected in series actually add up to give a net value. Also, if they were connected in parallel, whether the formula 1 upon R net is equal to 1 upon R1 plus 1 upon R2 is indeed correct or not. Do you think instead of having just 2 resistances, you had more than these, say 3 or 4 resistances? You would go the same way and find out the combination using 3 or 4 resistances. You could combine them all in parallel and get a new value for the combined resistance. Check out whether they also show you that the formula that you have been using in your work and in your study, that the combined resistances in series is just addition of each individual resistance, and whether or not the resistance in parallel formula is correct or not. So, this will verify it for you. What precautions do we need to take? Very much the same as what we had done earlier with the meter bridge. That means all connections need to be very tight and neat. Around a terminal, we should never connect by taking the wire round and round. It just adds to more and more resistance, besides being a bad contact and taking away the pitch of the screw on which you tighten it. Also, you should take care that you remove the insulation before you connect. Use a sandpaper to clean up the ends and terminals so that the connections are actually happening. That you use suitable resistance box for which you are finding out the resistances. That means, as we said, that it should be your guess how much this value of resistance is. In case you know it, then it is very much simpler. All you need to do is to combine them in series or in parallel and go ahead with your experiment. So, today you have learned how we can use the meter bridge in its balanced condition and use it to verify the laws of combination of resistances both in series and in parallel.